Okay, so in the last lesson, we derived this criterion on invertibility of linear bounded operator between two Banach spaces. The criterion says that A is invertible if and only if A is bounded below and A prime is injective. Now we want to write this condition in terms of a bilinear form. So we assume that we have X and Y Banach spaces, and we have a bounded bilinear form defined on X and Y. Bounded means that this supremum is finite. And once we have this bilinear form, we're going to define this linear operator from X to Y prime. We need to note that now actually we have to take the range space as Y prime, or codomain space as Y prime. We define the action of A on X, right? AX is supposed to be in Y prime, so we have to we define AX by its action on an arbitrary element Y, and we just simply define that by this bilinear form applied to the pair XY, and we can prove that we can see that this operator A is bounded very easily, because so AX, this we have to measure the norm of AX in Y prime, and the standard norm in Y prime is this the supremum norm, and we see that this is bounded by A times X. So the norm of A is bounded by the norm of little a. Actually, we can actually prove that the norm of A is equal to the norm of this bilinear form. Okay, so note that now the codomain is Y prime, and we know that in the criterion here we need to look at A prime. So which means A prime is going to be, let me write here, A prime will be from a Y double prime into X prime. So for convenience, it would be convenient if we assume Y is reflexive. In that case, this will become just Y. Okay, so we're going to actually assume that Y prime, assume that Y is reflexive. So if Y is reflexive, meaning that Y double prime is equal to Y, then the transpose of A is given by so this is the definition of transpose of A. Then we apply the definition of A itself in terms of the bilinear form little a. So that would be our transpose of A. And let me note that we also have the norm of A prime equal to the norm of small a. Now, bounded below properties are important. Let's write the bounded below property in terms of the bilinear form. Okay, so the operator A is bounded below if and only if now this is just the definition of bounded below. Now let's write this norm in terms of the bilinear form. So that's the bounded below property. We can also write this in terms of an inf-sup condition. Inf-sup y in y, axy divided by x y. We want this to be strictly positive. Similarly, we can also write the bounded below condition on a prime let me write directly in terms of the bilinear form. Now it's just the y is on the outer infimum and x is on the inner supremum. So that would be the bounded below property for a prime. So, well, if we want to now check invertibility of A, what we need is bounded below property on A and injectivity of A prime. But we also have an alternative condition that says that A is invertible if and only if A and A prime are both bounded below, right? So we can also use this condition to check bounded below property of A prime. So these conditions are usually called inf-sup conditions. Here, these are called inf-sup conditions. Let's try to write the injectivity of A prime in terms of the bilinear form A, because it's important. So A prime is injective, means whenever A prime is 0, implying y equal to 0, right? And this is now equivalent to, now let's write A prime y equal to 0 in terms of the bilinear form. That would be to say that this is equal to 0 for all x from x. So this alone is just we are just writing A prime y equal to 0. Now this should imply that y equal to 0. So that's the injectivity condition. So the theorem says that the operator A is invertible if and only if the inf-sup condition for A is satisfied and A prime is injective. And A prime, the injectivity condition is can be written in terms of the bilinear form in this way. So that's our main theorem. Also note that the second condition here, the injectivity, can be replaced by the inf-sup condition for A prime, which is basically this condition. The condition is very similar to the first one, except that you have y on the outer infimum and x on the inner supremum. But this injectivity would be usually it's easier to check than inf-sup condition. Okay, now let's write one simple corollary, which is the Lax-Milgram lemma. In some sense, you can think of this as the basic example. Okay, so in the Lax-Milgram lemma, we're going to take x and y equal to each other. So let's just take one Banach space and bounded bilinear form which is coercive. Coercivity, or actually it's a strict coercivity, means we have this inequality. for some strictly positive constant c. Then this linear operator A sending x to x prime defined by as before, defined by this condition, is invertible. Okay, proof. Take x equal to y in the main theorem. So what do we need? We need to check the inf-sup condition first. So let's say x is given, then supremum, so we're looking at the inner supremum here, is bigger than ax x divided by x, because, well, it's supremum, so we can put any y we want and we're going to get lower bound. And by using the strict coercivity condition, this is bigger than c times x. So this alpha constant that we defined in the inf-sup condition is bigger than c. Now, what about injectivity? For the injectivity, it would be the same, because okay, so let's actually look at, just instead of injectivity, let's look at the bounded below property for a prime, or in other words, inf-sup condition for a prime. So that inf-sup condition, for that inf-sup condition, we would have x on the inner supremum, right? So here we have x, and again we just replace put y in place of x. Again we have this inequality. So that's inf-sup condition for a prime, that the constant that we defined, beta, again bounded below by c, and so this is bounded below condition for a prime, so that implies that a is invertible. Okay, let's look at one example on the Lax-Milgram lemma. And of course, the power of Lax-Milgram lemma is it can handle non-symmetric problems. So let's try to look at one non-symmetric problem. So let's take x to be h10 with omega some nice domain. Let's say a bounded domain. And let's take the bilinear form, a to b integral uv plus b dot u times v. Okay, so you can immediately see that it classically it would correspond to this problem. Minus Laplace u plus b dot nabla u equal to f, some right hand side in omega, and u equal to 0 on the boundary of omega. Here we are thinking of b as okay, let's take b as a constant vector field. Okay, so the main thing is now, of course, we want to check the condition of the Lax-Milgram lemma. The main condition is now we want to look at this. So It's equal to integral squared plus b dot nabla u times u. Now we want this to bound this from below by some constant times the h1 norm, which is integral u squared plus u squared. Okay, now we know if there was no such, if b was 0, then we know how to handle this, because we have free Dixon equality. If b was 0, then we have the L2 norm is bounded by the H1 semi-norm for all u in H1 0. This implies that the H1 semi-norm bounds the H1 full norm, so some constant alpha u H1. Now the question is, of course, what to do with this second term. So to deal with this term, the non-symmetric term, we write this, just simply compute the divergence of this vector field b times u squared. Here u squared is a scalar and b is a vector, so it's a vector field. If you compute the divergence, you will have this expression. And now if you apply the divergence theorem or the integration by parts, you can see that the integral over omega u b dot nabla u equal to minus half integral omega u squared divergence of b, because u is 0 on the boundary, right? And now this means that if we assume that, actually we assume b is constant vector field, so the divergence of b will be 0, but more generally, if b is a divergence free vector field, then we see that this integral over here actually is 0. So meaning that AU is just simply equal to that, and we know that this is bounded from below by alpha squared u h1 squared. So the condition of all the conditions of the Lax-Milgram lemma are satisfied, and we have unique solution in this case.